Hey everyone, welcome to another tech video. Today we are going to cover RSA encryption. Uh, how RSA encryption works and how it is used for um, safe and secure transactions between two servers or two users. Right? You can also use that. Right? What do you mean by encryption, maybe, right? So you want to literally pass a set of secret to another person so that the person who's in between won't get to know what you are trying to say to the other person. I think we did all these things when in our childhoods. Probably we would have shifted the alphabets by n numbers and then say, okay, this is our secret number. So I'll send you all the ciphertext like that, and you get to know what I'm trying to say, but the other person won't. Those are a few small, initial steps that we could see, but those are easily, decodable or decryptable, if you want to say it. It's not a very secret stuff. Uh, so the concept revolves around something like trapdoor functions. So a function, if you apply that function on a number on a, let's say, private key, you'll get the public key. So from public key you won't be able to get the private key. So in Max, they call this as a trapdoor function. So you can go forward but you cannot come backwards, right? So you cannot do f inverse of x, right? So let's say to derive the public key, given a private key, so you call it an f of x. So you'll get the public key. So f inverse of public key should give you the private key, but f inverse of x is literally hard to solve. Right? So that's why we can exchange the secrets peacefully, maybe, right? Um, so this is simple explanation where you consider x as private key and x square as the public key. Someone who knows that you are squaring it up, so they can easily decode all these things. So this is not worth it, right? So the basic idea that revolves around private public key. So how are you going to use these private and public key, maybe, right? So use, let's say you have a server A, server B, and use the server B's public key to encrypt the message, and server B uses its own private key to decrypt the message. Given the public key is public, right? No one will be able to decrypt or no one will be able to come up with a private key. If someone was able to come up with a private key, then the security is compromised. But it is impossible with the computation power that we have as of now. So how all these things comes together, right? Maybe. So this goes with prime numbers, coprime, Gaussian functions, all these things. So let's say we have a prime number and its Gaussian function is p1 minus 1, or p2, so it is p2 minus 1. So relatively prime numbers, how many relative prime numbers are those are the that is what we call a Gaussian function. So let's say p1 and p2, so then the Gaussian function is phi of n, p1 minus 1 and then p2 minus 1, and we expose the n towards the public, right? And then if from n they have to find the p1 and p2 to derive the Gaussian function. It's really hard to factorize n when it is 2048 bit. Right? It is a very big number, and factorizing a very big number and finding all the primes, it's not really hard. I mean, it's not really easy. It's really hard. So then we comes to all these Fermat's and Euler's theorem, right? Here one of the theorem that the state is at e to the power of I of n is equal to 1 mod n, right? Given that A is a coprime twin, right? And 2 to the power 2 is equal to 1 mod 3, right? 2 to the power 2 is 4, and 4 mod 3 equal to 1, and 1 is 1 mod 3. So that is the idea. So given you have a so from this concept, can we come up with something else, right? If we have a to the power phi of n plus 1 plus 1 mod n will be equal to a mod n, right? So what we want is a to the power 5 of n times, a to the power 5 of n, um, plus one mod n actually. So eventually what we are expecting is that we need two numbers, we call them as private and public keys. So k times d, that those are the variables that I chose. I think it differs from the standards. Probably check the standards. E and d are being used, and so k times d mod phi of n equal to 1 mod n. So what does this mean? So we take an arbitrary number k, and if we multiply, and we need a d such that d is the d will be k inverse of phi of n, right? So um, so k times d equal to mod phi of n is equal to 1 mod n. So which means that k times d equal to, let's say, r times phi of n plus 1 mod n, right? R times so uh, you know r times phi of n plus 1 mod n, 1 mod phi of n. So eventually 1 mod phi of n will be the result over here, right? So and d will be the k inverse of phi of n, right? So I think there are these concepts are available, probably how to take an inverse and all the modular inverse. I think probably we can look at CP algorithms and all those things to find all these details, right? So that's where, so once you expose, so what you need to expose is basically this n, because the server A can use this n for modular operation, and also you need to expose your public key, right? So let's say d is the public key, so a to the power d mod n, right? Now you will send it to the other user. Now a to the power d, the whole raised to k, so you are again exponentiating it by k. A to the power k times d mod n, you will get r times phi of n. That's what I explained earlier, right? Because k to the power k times d is equal to 1 mod of phi of n, which means that r times phi of n plus 1 mod phi of n, right? So it's r times phi of n plus 1. Now you can say a to the power r times phi of n mod n times a times a mod n actually. So a to the power r times phi of n mod n will be 1 because of this theorem, right? Finally you will get a mod n. That is your answer, right? Why it is not possible for someone else to snoop in and get our message? That's the reason. You have a 2048-bit encryption, you need to factorize, which is not possible with the current computation power, right? And NE is public and ND is private, so that is the standard notation. Okay, so let's go into the code actually and see how we are how computer system might do this, all of these things. So this is RSA, so crypto slash RSA, this is some package that is already present. Generator 2048-bit private and public. So you have a private public, you have a message, you have to convert into integer, and if it is greater than integer, you have to handle it again, right? Greater than or equal to n, then you need to reduce. You need to get it sorted, because if it is greater than or equal to n, then you need this set of operations to do that. Finally you will encrypt the message. So how are you going to encrypt the message? To the power e mod n is what encryption is. And so you got m to the power e mod n over here, which is c. So the other server, let's say server B, use c to the power d mod n, which is actually m to the power e times d mod n. Now once you have that you multiplied e and d, and you came to expression, right? Now we are going to check whether all these things are matching or not, right? So what is c? It's printed over here. What is m1? That is printed over here, right? What is m2? That is printed over here, right? And then what, since we have taken m to the power e times e times d mod n, this is our decrypted message, right? So finally, we are printing the message if m dot cmp m1 equal to 0. Recovered message is m1, right? So m1 is here. Okay, sorry, I think I pointed it here, but yeah, m1 is over here, so that is we took the power, so which is, m to the power a times d mod n, something like that. Right? Now we have the message that will get printed over here. Right? So let's run the code and see how it works. So this is N, this is E, this is M. So hello ghost store got converted to this. We have a C, so we have an M1, we have an M2, and M equal to M1 true, M equal to M2 true, yes, and recovered message M1, which is hello ghost store, right? We have printed M here, so this from the M we recovered the M1, here. So that's the simple thing about RSA. I think that's it for this session. Bye bye guys. Take care. Have a great time.